We are taught that the foundation of geometry, the principle that a squared plus b squared equals c squared, was discovered by the ancient Greeks. Yet this exact mathematical relationship was formally codified at least 3 centuries before Pythagoras was born. Around 800 BCE, an Indian Vedic sage and master craftsman named Baudhayana recorded this principle. He authored the Baudhayana Sulba Sutra, the Rules of the Court, a technical manual for large-scale engineering. The birth of rigorous geometry was driven by the high-stakes physical requirements of ancient Indian masonry. This image shows a render of an Agni Kayana, or Vedic fire altar, constructed entirely from baked bricks. These altars were built in highly specific geometric shapes, like this falcon. Ritual rules required priests to change the shape of an altar, transforming a square into a circle or a falcon, while maintaining the exact same area and volume. Any error in measurement was considered ritually unacceptable. This zero tolerance for deviation forced these builders to invent highly precise mathematical algorithms to ensure exact equivalence. Modern mathematicians, including Dr. T.A. Sarasvati Amma, have analyzed the Sanskrit verses of the Sulba Sutra and demonstrated that they contain sophisticated solutions for linear and quadratic equations. Religious constraint acted as a direct catalyst for mathematical rigor. Geometric precision became a strict spiritual mandate. Looking at this diagram of the Sulba Sutra's 12th shloka, a rectangle is measured by a diagonal chord. Baudhayana's method extrudes a square from the length and breadth, representing a squared and b squared. A third square produced by the diagonal perfectly matches their combined area, representing c squared. This proof bypasses the need to measure internal degrees. It relies entirely on calculating physical area using ropes. This physical, area-based manipulation contrasts sharply with the later Greek method, which relied on theoretical, axiomatic proofs drawn on a flat plane. By visualizing mass and area, Baudhayana natively solved complex algebraic relationships centuries before the invention of modern algebraic notation. The earliest knowledge of right angles can be traced to Egypt around 2500 BCE, where builders used knotted ropes pegged at ratios of 3, 4, and 5 to ensure square corners in their masonry. By 1800 BCE in Babylon, scribes were recording advanced arithmetic lists of Pythagorean triples on clay tablets. A Pythagorean triple is a set of 3 positive integers that strictly follow the a squared plus b squared equals c squared rule. Knowing a specific working ratio like 3, 4, 5 is a practical construction hack. It is entirely different from stating a generalized mathematical law that applies to all possible dimensions. In 800 BCE, Baudhayana provided the first formal statement linking these arithmetic ratios to the universal geometry of all rectangles, regardless of specific lengths. Pythagoras provided a formal logical proof in 518 BCE, but Baudhayana is responsible for the first explicit, codified formulation of the general theory itself. This diagram illustrates another strict constraint: doubling the square. Builders had to create a new square altar with exactly twice the original area. Combining 2 squares creates a rectangle, which must then be forced back into a perfect square containing exactly 2 units of area. Finding the exact side length of this new, larger square mathematically requires calculating the square root of 2. The square root of 2 is a non-terminating number. A craftsman in 800 BCE had to derive an infinitely long decimal value without a calculator or modern mathematical notation. This is an irrational number, a physical measurement that cannot be expressed as a simple whole fraction. Solving it required a radical algorithmic approach. Baudhayana's text states the algorithm directly: increase the measure by a third, add a fourth of that third, and subtract a 34th of that fourth. Here, a square with area 2 is sliced into 3 strips. One strip is rearranged along the edges, forming a near-perfect square with microscopic excess. Shaving exactly 1/34th from those edges forces the geometry to close into a true square. This physical manipulation of ropes and bricks maps perfectly to the algebraic equation: 1 plus 1/3 plus 1/12 minus 1408. The decimal value yielded by this sequence is 1.41412156. The true mathematical constant for the square root of 2 is 1.4141235. Baudhayana achieved accuracy to 5 decimal places through the rigorous fractional geometry of physical matter. Looking at this diagram of a square and a circle overlapping, we see the geometry used for a final ritual requirement, converting a square altar into a circular one without losing even a fraction of the original area. The builder draws half the diagonal from the center outward, describing a circle using a third of the segment outside the square. This proportion yields a ratio of 900/289, or 3.114. Alternatively, shifting the geometry yields 1156/361, or 3.202. While these ratios are approximations rather than an exact constant, they provided the necessary tolerances to ensure zero-error physical bricklaying. This early geometric conversion laid the groundwork for Aryabhata, another Indian mathematician, to calculate a precise pi value of 3.1416 centuries later in 499 CE. This method demonstrates an advanced ancient understanding of proportionality, specifically the insight that a circle's area is inextricably linked to the square of its radius. This summary slide details Baudhayana's holistic mapping of geometric properties. He successfully bridged arithmetic scaling with pure geometry across the theorem, the calculation for the square root of 2, and circle proportionality. The foundations of modern engineering and geometry are a composite of global human achievement, drawn from multiple civilizations over thousands of years. The Greeks played a vital role in formalizing axiomatic, theoretical proofs. However, rigorous algorithmic and applied geometric frameworks were already being actively utilized and codified by Indian scholars centuries prior. The algorithms documented in the Sulba Sutra remain mathematically sound and practically applicable today. In ancient India, the pursuit of spiritual perfection through strict ritual constraint necessitated the birth of the exact mathematical sciences.